Thank you very much. It's great to be here. I haven't been to Robinson before. It was a nice trip down here. I grew up in the northwest corner of Illinois. A lot more trees than in central Illinois, and it was nice to get back to a place that had such a nice mosaic of land use. I mean, corn and soybean is nice, don't get me wrong, but, and so is $13,000 an acre. So I'm going to talk about a long-term data set that we have on the Embarras River, and then feature one experiment that we're doing that was funded by the Nutrient Research and Education Council. Some of this is repeat from Lauren's talk, and so I'll go over it quickly, but if you're hearing it for a second time, it must be that important. So, we have a target of reducing N and P loading to our streams and exiting the state by 45%, but we have been given an interim standard, or an interim date of 2025, where we don't have to get all the way to 45%, but we will hopefully by 2035. And the goal is to reduce the hypoxic zone down below 2,000 square miles. It's often 5,000 to 10,000 square miles in area. And you saw something like this as well. This is from a paper that Mark David and I did back in '99, published in 2000, which was very similar to what was found with the science assessment that was recently done, that on a statewide basis, sewage effluent accounts for 16% of the nitrogen, where phosphorus is much more important. Sewage effluent contains a lot of phosphorus, and it's about 50% of the load is from sewage effluent. We've got a large population of people in Illinois, almost 13 million people, clustered around Chicagoland, and so the Illinois River receives sewage effluent from Chicago, and it's very important as far as the contribution from sewage effluent, and so it's much more important for phosphorus. If we didn't have Chicagoland in a more rural state, there would be a greater challenge to solving the phosphorus problem, because only a third of it would come from sewage effluent. But thanks to Chicagoland putting so much phosphorus and sewage effluent in the Illinois River, we have more of an equal balance between point and non-point pollution for phosphorus. But agriculture is predominantly responsible for the non-point source pollution of nitrate. And you saw something like this as well earlier. There's 8 major rivers that are monitored, and that's how we calculate how much N and P leaves the state. And you can see from the non-point source being the cross-hatched area that only the Illinois River has a significant point source, and much of it's non-point for nitrate. And again, for phosphorus, you can see that the Illinois River has a lot of the total phosphorus. But overall, about 20% of the nitrogen is from sewage effluent, 80% from agriculture, or at least non-point, which is mostly ag, because there's not much that comes from urban or golf courses or forests, and but it's about 50-50 for total P. So nitrate is predominantly conveyed from field to stream through tile drainage. We have less tile drainage down here. It's a little different. I've tailored my talk to be more relevant to southern Illinois, but I work in central Illinois where it's dominated by tile drainage. Overland runoff is much less important for nitrate movement because rainwater has very little nitrate in it. And when precipitation rates exceed infiltration rates, we have runoff, and runoff then is essentially rainwater with very little nitrate in it. But phosphorus is a much different story. Phosphorus is an overland runoff source. It's when rain picks up soil sediment and moves that overland and into the streams. That is the main source of phosphorus to our streams. And so soil erosion is very important, but also unincorporated ammoniated P fertilizers are a source. Since we're taking tile drainage water samples, we analyze them for nitrate. If you look for phosphorus, you will find that as well. It's not as predominant of source, but it is an important source in the heavily tile drained regions. And then I'll come back to this. It's hard to see that picture right there, but that was a rain on snow event. So snow is melting and it rains and the soil is frozen. That's a worst case scenario for when we lose our ammoniated P fertilizers if it was broadcast on frozen soils or snow. Here is an example of nitrate in tile water with 3 successive flow events in a row. The flow is in liters per second. You could divide that by 4, and so this is a very high flow, about 6 gallons per second out of a 12-inch tile. And you can see the first event has much of the flushing of the nitrate. So nitrate was available in the soil to be flushed. It moves through preferential flow channels and gets into the tile. But the next 2 events, which these are just 7 days apart, we got a little spike of nitrate in the second event in both of these tiles. These are 2 adjacent tiles under the same production practice. But by the time we got to the third event, we showed dilution at high flow. That's very typical of nitrate. So after a dry period and all the fertilizer's been on and it's been nitrified, that's when we'll get a pulse. This happened to be the first big event after fertilization that year. Now this is the same 3 hydrographs, same 3 events, but this is phosphorus in tile water. And let's go back. The magnitude, we're talking up to 50 part per million nitrate, 10 to 50, where phosphorus is about 100 times less than that. So we lose a lot less phosphorus, but yet it's still important to sensitive water bodies, especially reservoirs that are used for drinking water. But the difference between nitrate and phosphorus is phosphorus comes out high concentration in each of these 3 events. There's just more to be flushed out each time. So, but it's all about flow. So once flow goes down, then the phosphorus returns back to a low baseline concentration. So a very different movement of nitrate and phosphorus in the soil, but they both can end up in the tile. And here's another slide you've seen, but this is to put into perspective where we're losing our nitrate versus our phosphorus. And this is non-point loss, non-point source. So again, it's the tile drained regions that have the most. I'm going to be talking about the Embarras River. That watershed is right here. It's not the highest, but yet where we're doing our sampling by Champaign-Urbana, nitrate loss is quite high there. And in fact, as the river flows through less agricultural land, the folks in southern Illinois are actually diluting the nitrate concentration. It makes the Embarras River look better. So I'll give you guys credit for diluting the Embarras River because it looks worse when we're just talking about up there. The dark blue is loss of 25 pounds of nitrogen per acre per year. That's quite a bit. Now the highest for phosphorus, this color down here, that's a loss of about 2 pounds per acre per year. So very different magnitude of loss. And if you look at the 2 across the state, this is a northern 2/3 of the state problem because of tile drainage. Not much of a problem down here, but if we continue to add tile down in southern Illinois, that probably will move more nitrate from our fields. But phosphorus is more about overland runoff, and therefore when we get into the hillier land, there we're more vulnerable for loss. Here is a close-up of the Embarras watershed. That puts us on the U.S. map. The Embarras River drains into the Wabash, and which drains most of Indiana. Here's a close-up, and our research area is just the upper Embarras at Camargo, Illinois. And here's what the watershed looks like, and here's some statistics on it. 119,000 acres. The headwaters are in Champaign-Urbana, but the sewage effluent goes into a different system, goes over the Vermilion. It's very flat topography. The shape of it is some moraines, glacial moraines. The nice thing about studying this watershed is that it's 90% row crop. There's very little other use of the land. There's very little municipal waste, so we don't have to sort that out. Very few animals, very few fences left in that area. Very little livestock, so we don't have to try and tease out the effect of manure in this watershed as well. So we can be quite sure that it's a row crop influence. And we're heavily tile drained in that area, and we've gone to pattern drainage in the last 5 to 10 years. Now, the benefits of a long-term data set are numerous, but the thing that we all want to show is an improvement in water quality over time. So we have to know where we're starting. And with 22 years of data on this one river, we have a very good baseline. It'll also allow for the quantification of any environmental changes, such as if we get wetter in the future, or if we get drier. I think the models show we might get wetter in this area. And it'll allow for quantification of any changes in land use or management. Let's say we start using cover crop a lot more throughout the state. Well, we should be able to see that effect in this data set. But it also will reveal unusual events or years that are very different than other years. And then ultimately we'll feed this all into a model, and it'll help us predict the future. The USGS, United States Geologic Survey, they are the experts on gauging flow on our rivers, and they do it at many, many locations throughout the state, not throughout the country. And they use bridges as their weir, or you could think of it as a flume. So this is a geographic or geometric shape here that doesn't change much, and the height of the water then is related to the flow. And they're out there checking that every 6 weeks. And so that's the bridge where we've sampled over the last 22 years, over 1,250 times. Our lab group has gone to that bridge and dropped a bucket and a bottle down into the water column and pulled it back up and analyzed it for nitrogen and phosphorus. So this is what USGS provides online. This is the hydrograph from the last 22 years. And you can see there's two really high events. 2002 was a very wet year. And in April of 2013 was the biggest event that we had at Camargo, over 7,000 CFS that day. Huge event, lots of nitrogen loss. And, but you can see how dry 2012 was. 2000 and 2001 were also very dry. And river load depends greatly on the amount of water that goes down the river. So in a dry year, we don't lose very much nitrogen. That might only be 5 or 10 pounds of nitrogen per year, or 5 per acre per year. Where in 2002, the entire watershed lost 50 pounds of nitrogen per acre. But that followed 2 dry years, so obviously there's some carryover of N from previous years that then flushed in 2002. If you add up, these are in cubic feet per second, so if you add that up, on average, 5.6 billion cubic feet go down the river at Camargo a year. And how to put that in perspective, I looked up what the Empire State Building's volume is. So we could fill 150 Empire State Buildings every year from this little stream, 119,000 acres being drained. This is the nitrate data set. I took the very first sample back in '93, and we've continued on through this entire time. One thing that stands out is each year we go down to a very low level, and that is when the tiles stop flowing in August, September, and October. The river quickly goes down to less than 1 part million nitrate. So it's very, very obvious in our area that tiles control the nitrate conveyance to these streams. But something else I want to point out is 2012 and 2013. 2012 being a drought, we didn't have to take as many samples that year because we sample weekly if there's no events. If there's an event, we go out and sample as much as 2 or 3 times a day. But following the 2012 drought, we had the highest concentrations over that entire time. And it was the highest flow-weighted mean nitrate concentration. So it's really the 1-2 punch. You have a 50-year drought followed by the wettest January through June that we had ever seen. And that's a bad combination for nitrate loss, no doubt about it. But 2002 doesn't really stand out as any different, but there's so much flow that year. That's what led to that 50 pounds per acre N loss for every acre in that watershed. So it's a conservative estimate because we're not accounting for small towns and roads and pastures. It's just, we just divide by every acre in the watershed. So this is why I was asked to be here today, because I wanted to talk more about phosphorus. I'm a guy that's been chasing water for 20 years, and mostly I look at nitrogen, but we have all this phosphorus data, and we're compiling it right up until yesterday, because we want to get this word out as well. So you can see that on occasion we have very high events. This is dissolved reactive phosphorus. That is really just a convention. Let's just think of it as dissolved phosphorus. And this is a very high event, and that's a February event. This one's in February, that one's in February, and that one's in February. It seems like when we have snow melt, we get the highest dissolved phosphorus. And I think that could go back to us applying ammoniated phosphorus fertilizers on frozen soil, and what's worse is putting it on snow. And this was the day that had the highest ammonium we've ever seen in the 22 years, and it really stands out as an unusual event. That year, December, the soils froze early in December and were frozen throughout January, and then we had rain on snow January 31st, and that spiked, but the ammonium was higher than ever before. That has to tell you something, that it's ammoniated fertilizers. But on some of these events, the particulate P is really high. That means soil erosion. So we can take this data set, and we're going to continue to work on this. I think we're going to be able to tease out the difference between soil erosion events and these winter thawing events. But also, this event happened to be right after fertilizer application. That was late November. So that was a heavy thunderstorm in late November after a lot of fertilizer has been put on. So we can lose it any time of year, but the worst cases seem to be with snow melt. You do pick up a little trend that's exactly opposite of the nitrate. That happens to be at very low flow. We pick up the signature of the sewage treatment facility or the phosphorus released in a small town about 10 miles upstream from us. But we can sort that out. We know what their contribution is. So it's interesting to see that almost every event over 0.4 is a late winter or early spring event. That's when we're losing our phosphorus. But particulate P can happen anytime, and that often is in June and July with heavy thunderstorms. So if we can cover our soil, till it less, incorporate our fertilizer, we should be able to see a trend that we are making progress here. I want to say that with the nitrogen data set, we see no trend, which is good. It's not getting worse. We've put a lot of tile in the last 10 years, and this is not any worse than it was. If we put a trend line through that, it's flat, which is good. I mean, we'd like to see it going down. There's certainly been lots of conservation efforts. There's riparian buffers that have been put in. But we believe that the improvement that we should see from conservation practices, or the improvement in our overall balance, meaning our yields are increasing, we're removing more N from the field, our simple field N balances have improved. Why aren't we seeing an improvement in the stream over time? I think it's because we keep adding pattern drainage. So we're masking our benefits of higher yields and conservation by adding more tile. But at least we're holding our own in the face of all this tile drainage coming in. So I'll twist that into a success. Now here's the Embarras River at Camargo during a very, very high flow event. And the water is very muddy. That's one of these heavy thunderstorms that dislodges soil particles, and If you see heavy sediment load, you know that it's a very large phosphorus load, and it came from soil erosion. And we hate to lose soil. Our topsoil is our most fertile part of our rooting zone. But this is that event I referred to earlier. This was January 31st of 2001, and this was absolutely the highest phosphorus and ammonium we have seen in a whole host of watersheds that day. We were looking at least a half a dozen watersheds that day, and the phosphorus and ammonium spiked on that day. In fact, we saw phosphorus at 8 part per million. You know, I was talking earlier that the magnitude is like 0.1 to 0.5. We saw 8 part per million coming out of this field and 10 part per million ammonium that day. So we really don't want to put anything on snow. You guys don't have as much snow down here, so you may not have as much of a problem with that. I want to discuss end of pipe or edge of field remediation techniques very briefly here because you have less tile drainage, and they don't do anything for phosphorus. These are nitrate remediation techniques. So that's a little disappointing that they don't help for phosphorus. But of the three, the constructed wetlands do the best for nitrate removal. However, there are very few people interested in putting cropland underwater. So we've had essentially no takers. We've got a nice study. We had a 3-year study back in the 90s, shows we remove about 50% of the tile nitrate in that wetland. We came back 20 years later. This is our 3rd year of looking at it again. 20 years later, the wetlands are still doing just as well as they were back in the 90s. But we do not have many people interested in that technique. Bioreactors are seemingly more popular because they have such a small footprint. They're maybe 20 feet wide by 50 feet long and to the depth of the tile. And they can remove some nitrate, but they can easily be overwhelmed with high loads and high flow. And at high flow, the wood chip bioreactor is bypassed. So, because we're not blocking the tile, we're just diverting the water through the wood chips. So really high flow goes right up and over the stop logs and goes untreated. And in 1 year, 50% of the tile flow bypassed the wood chips. So no removal there. But they do hold some promise. The cheapest thing to do is just put a control structure out there and block your tile. The drainage water management has some promise, but not as much. I mentioned April 18th, and we were doing these end of pipe remediation techniques. They were all flooded. They didn't do anything for us that day. The only thing that worked were fields that were either no-till or strip-till or cover crop. So you've heard about 4Rs, but cover crops are in field as well. That possibly can help with nutrient loss. But in-field remediation for phosphorus, less tillage, incorporate your fertilizer, grass waterways, contour farming, water and sediment control structures or basins, and cover crop. Definitely should have some waterways if you've got sloping land. Riparian buffers in our neck of the woods, or our area, are short-circuited by tiles. They look great, they hold in some soil, but the tiles go right through that, so there's no benefit. More benefit down here. Cover crops. The classic example of why we use cover crops is to protect the soil. But we're going to add some organic matter. There's some idea of suppression of weeds. But we were interested in it, can it reduce the tile nitrogen loads? So I'm going to briefly tell you about an experiment that the Nutrient Research Education Council is funding. And it's testing one of the strategies in the nutrient loss reduction strategy. And it's a longer rotation, so we've got corn, soybean, wheat. That's different for central Illinois. We've got cover crops, and we've got bioreactors. And it's real world. These aren't small plots. This is 55 to 70 acres. And after corn, we're trying cereal rye. After soybean, it's winter wheat. After wheat, we tried a cocktail of cover crops. It was turnip, radish, and red clover. And if you can sow your cover crop in August instead of September, you can get tremendous biomass. That's our challenge as we move north. We don't have enough growing season for cover crops, so we're trying to get it planted in standing corn. and that's hit and miss if you don't have the moisture. So if you can drill it, you can get tremendous biomass. Here's what the cocktail looked like up close. Yes, there is some red clover in there, and we hope that does well this spring. But as of right before our first frost in November, when we looked at our biomass, we had tremendous biomass, almost 3 tons above ground and below ground, because we pulled the radish and turnip out. And you can see the individual biomass. This has got over 100 pounds of nitrogen per acre in the biomass. And it drove the soil nitrogen levels down to as low as they go. The lab returned the results, and it would say 1 part per million from 0 to 1. 1 part per million from 1 feet to 2 feet. That's as low as they go. They don't give you a 0. And so what did it do to the tile? Here's that tile that had wheat, went all the way up to 13 parts per million nitrate. After we had that cover crop biomass growth, we're down below 1 part per million in that tile. Most people didn't think that was possible, to be able to have that kind of influence on a tile in 1 year. But it just shows proof of concept that we can have a major impact on nutrient loss if we can keep living roots on the landscape longer. So here's my conclusion slide. I've gone over most of this. But to frame this a little differently, we're not losing that much phosphorus. It's only 1 to 2 pounds per acre. It's not affecting our bottom line, but it's having impact on water quality. So this is a harder problem to solve than nitrogen, because if we lose enough nitrogen, yield will actually go down and there's feedback. But here we lose phosphorus and no agronomic reduction in yield. P-loss, I say this is the hierarchy of the way we lose it in Illinois. Soil erosion is still the most important source of phosphorus. We've got to try and minimize soil loss. We should incorporate our fertilizer. Yes, tiles have phosphorus. Don't apply fertilizers on snow. Don't put anything on snow, would be my recommendation. The mixture of cover crop planted in August really took up soil and reduced tile nitrate load. But of all of the things that we can try on our fields, the only thing that will possibly reduce both nitrogen and phosphorus at the same time would be cover crops. I don't know of any other, those other end of pipe techniques. That's just for nitrate. And some things we can do that are just for phosphorus, like incorporating the fertilizer. But if we put a cover crop out there, we get the benefit of less soil erosion, and the cover crop can take up any nitrogen that could be leached. So that's all I have for you today. I thank you very much for having me here. Appreciate it.